So we have this question here. We're doing question 3 from the 2015 exam. And it asks about concentration. There are multiple things in this problem, actually, to realize. So yeah, it's asking about the concentration. And I want to turn your attention to the units. You see, concentration, it's, how much of something exists per volume, typically per volume. That's really the only way you can measure concentration, how much of something is in a given space. And you can see all the answer choices are in M. M is very different than italicized M. Like, there's a reason this is italicized, because this M already means something. M means moles per liter. You can already see this is take 2 of the video. So you have moles per liter, and it's asking for the concentration of the nitrate ion. So we have 32 grams of magnesium nitrate, and that's really significant because that's very different than just nitrate. Nitrate. It's asking for the nitrate ion. And you can see there's 2 nitrates per magnesium, so there's 2 nitrates per molecule, is what I mean. And funny thing, we know these are nitrates that are, like, dissociated as ions, because it says it's an ion, so it means it dissolved in the solution. Ion means either gained or lost an electron entirely. So this had to have been, put in water and dissolved, where this one, I know, gained an electron. Both these gain an electron. That's just a little side note. Should help you better understand. So you have two of these, like, random particles that are dissolved in this solution. So NO3 minus NO3 over here minus. This is 1 mole atom. This is another huge atom. This is magnesium. Lost 2 electrons. Yeah. And we kind of want to know. How much the concentration of these nitrates, nitrate ions. Yeah, so we know there's 32 grams of this. In order to, like, get an atom amount, it's always just good to transfer this into moles. So even though this is, like, tied with the mg, if we convert it into moles, then we can more easily we can more easily just get the nitrate. So let's do that. It tells you also, by the way, the molar mass is over here. So, it clues you into the fact that you have to use the molar mass in your calculation. Or else you're doing it wrong, probably. So 42 divided by 148.3. So you get 0.216-ish. And yeah, so 32 divided by that many grams per moles. And that's like it kind of makes sense. Like, there's this many grams in 1 mole. So if you have this many grams, you probably have this many moles. I like to try to make sure it just makes sense. So 0.2616 moles of this. And you're kind of almost there. So you have that many moles of this molecule. So it's good to just rewrite. Make sure you rewrite all the information. So you have that many moles of this molecule. Well, each of this molecule has 2 nitrates. So you have 0.21 moles of the molecule, but that means you have twice as many moles of the nitrate, if that makes sense. I'll restate in a different way. Like, if 0.216 moles, which means, let's say you have that, let's pretend that means you have that many atoms, okay, of MgNO3, because that's what it means, except it doesn't mean, it'll mean like, let me actually convert it into just atoms, and it'll be accurate and easier. So if you have 0.26 moles of this, that means you have, let's see, so you have 6 moles of MgNO3, 2. Well, there's, in 1 mole of anything, there's 6.02 times 10 to the 23rd. And so you're gonna have, like, that many atoms, however, that doesn't work out. You're gonna have, like, oh, that didn't work out either. Okay, yeah, so we're gonna have to just calculate this real quick. So yeah, so 0.46 times 6.02 times 10 to the 23rd, so multiplication is like a separate, okay, so 6.02 times 10 to the 23rd, so in 1 mole you have this many atoms. 1 mole of anything you'll have this many atoms. Now, we have this many moles, so that many atoms per mole times this many moles, you have this many atoms. I know this is going to be like, it's actually going to be like 1.3 times 10 to the 23rd. This works. Atoms of MgNO3. Okay. So you have that many atoms of this. Well, for every, oh sorry, well, molecules are atoms. It doesn't, like, if it's one thing, it's gonna be an atom. Or, if it's, if it's just like O, then it's an atom. Two, that's a molecule. But so same meaning as what I meant. So you have this many molecules. You have this many of this molecule floating around, or existence, except it's dissolved, slowly separated. Or you're gonna dissolve it. Well, so that many atoms, well, I mean, that many molecules, well, for every molecule of this, you have 2 molecules of this. So I feel like this might help build some sort of intuition, I guess. So you can just multiply this by, okay, for a molecule of that, you have 2, molecules of NO3 per molecule of Mg. So the units are going to still cancel out. And we're just going to get an answer that we can actually just convert into moles. Again, this is just ultimate intuition. I wouldn't do this on an exam. I would just straight calculate it, like how I had been doing it, where I had just this and I multiplied by 2. But I want to just build a little bit of intuition by showing the atoms, and you get this, which you don't actually. You get oh, yeah. I don't know why I hit equal again. Yeah, so you get this. I just wrote the same thing. twice or something. So yeah, so that many molecules times this many molecules of NO3 per molecule of this, you get that many molecules, and NO3, and you know, that is going to be a certain number of moles. Because again, mole is just a number of atoms or molecules. So mole is 46.02 times 10 to the 23rd molecules. It's going to have what? It's going to be, I think, the same. Wait, is this correct? Went down, I went up 1.3 times the 23rd. Sorry. Yeah, so 2.6 divided by 6.2, 10 to the 23rd, just make cancel out each other. You get 0.43, which is what I had gotten over here just by multiplying this by 2. So I was like, okay, how many moles of this times, well, you have 2 moles of 3 per mole. There's 2 molecules of that. So let me take a little process. So we had that. Add that. So oh, that looks awful. Yeah, so you had two, I'll make it a little more obvious that it's a number. So you had 0.0216, you just multiply by 2, and you get 0.143-ish. And yeah, I can already say this. You have that many moles of NO3, and then you can say, okay, so you have 0.43 moles of NO3, and this is in 425 milliliters. And it was this is per 425 milliliters. But we want it in a density of moles per liter. So we just have to convert this. If this was, you just had to convert this into liters. Off the top of my head, I would just be like, okay, that's that many moles. Kind of. Oh wait, yeah, that's that many moles of NO3 per liter. I mean per 0.425 liters, because I know, yeah, that this is equal to 0.425 liters. But to explain away, like just converting this into liters, you just have that many milliliters. There are 1,000 milliliters in a liter. This is like 1,000. Each of these are 1,000th of a liter. So I would divide the bottom by 1,000, which I guess is the same as, well, if I were to do it in the, I guess, the stoichiometry way, again, because everything I'm thinking is like kind of just mental math, like, okay, this is 1,000, so I just gotta kind of divide this by 1,000, because this is supposed to be that much smaller, right? That, but yeah, to do the more stoichiometry way, you'd be like, divided by, so that many moles left per milliliter, You would just get this just by canceling out the symbols. I just can't think of like a simple way to explain that. Like if you're gonna take 1,000, if you're gonna divide this by 1,000, it's like you're multiplying the numerator by 1,000 because like this is a fraction, so it's like just a comparison, I guess, between two numbers. That's kind of what fractions are kind of like. No, that's just what fractions are, honestly. In one way of thinking about them could just be a comparison between two numbers. So if you're going to divide the bottom by 1,000, you're just multiplying the numerator by 1,000. And you can just test this. Sorry, this should be multiplication, not a division. You can test this by just canceling out the signs. So you have milliliters on top, milliliters on bottom, those cancel out. Liters on bottom, okay. So multiplying by that 1 over L, so it's just going to stay as 1 over L. And so, yeah, so there's just that, and you just get, well, if you did this, you get 430. Over 425 liters, which reduces so we can, let's have both of these, right? You'll see they reduce, again, fractions are just comparisons between numbers, so again, don't get too fooled by the stoichiometry, the confusion, like, you're really just trying to rescale. So you multiply the top by 1,000 because you're trying to scale this into liters on the bottom, which is 1,000 times larger. Or you can think of it as making the bottom, just making the number 1,000 times smaller, but putting the unit that's 1,000 times larger. At least two would be the same thing. Just divided by 425, 1 point whatever, 1-ish. 43 divided by 0.5, same thing, it was open. So same thing, literally the same thing. So these are both the same, if that makes sense. I'll probably redo, So, okay, yeah, whatever. So, yeah, then, you just do, oh, yeah. So, you can, so let me just redo this part again, because I think this is a very prime example. So, if you have that many moles, of 425 milliliters, you could say, okay, I want to convert this into liters, so the first thing you can do is just trying to make the symbols make sense. Maybe try multiplication first and then try division, or whichever one, seems like is right. Actually, whatever. So multiplication and division first, see if it works. So I'm going to start multiplication. I just want to see the signs are toxic. It's just like straightforward, but I feel like kind of time, okay? So, maybe we just put it in. And then you're just going to say, okay. So multiplication, so these are just going to stay the same. Like, let's say this was division. Okay, let's say this was division, okay? Even though this is on top, you're like dividing. It's like an inverse process. There are many ways to like illustrate this. But yeah, it's like just an inverse process, and so everything here is kind of flipped. So you could turn this into multiplication and flip this, and you would do the same thing. so you divide, so you take this, that, and then you can just divide this by that to get how many moles per liter. Same thing for the other one. If you want to around, moles per liter. And you just get the answer. It's about this, because I did a little bit of rounding. And yeah, and I already saw the answer as the so that's good. That's number 3, and hopefully things have been clear along the way.